Right, so thank you all for coming. My name is Eric Evans. I work for the Wikimedia Foundation. Full disclosure, I am also a member of the Cassandra PMC, and there was a time when I worked on Cassandra full-time. That was my job. That is not the capacity that I'm presenting today. My time at the foundation has kind of given me the best opportunity I've had so far, at least for modern day Cassandra, to develop an application against Cassandra and to be involved in the operations of the cluster. And it's been quite an eye-opener, so to be on the other side of the fence. So that's kind of the frame of reference for this talk. The Wikimedia Foundation, well, Wikimedia in general, is an umbrella that represents a number of member projects, all sort of in the scope of free knowledge, collaboratively edited free knowledge. It is our mission for a world in which every single human can freely access the sum of all knowledge. The projects in total amount to over 16 billion page views every month. I believe it is my understanding that if you were to add up the aggregate traffic, that it would be equal to about the number 5th ranked web property. Wikipedia alone, at 38 million articles in almost 300 languages, 10,000 new articles every day, is ranked number 6 all by itself. So let's look at architecture a little bit, just to give some background. I'm going to build a use case and then talk a little bit about our use of Cassandra and sort of our experiences, but let me start with some background. One of those logos on the screen of all the projects was for MediaWiki, which isn't technically a free knowledge project. It's a free software project. It's the software that we host all of the wikis at Wikimedia. And it's kind of old school. It's a very mature application. It's been around for quite a while. And so, for all those people who jump to all the latest languages and frameworks, it's kind of boring. It's a LAMP stack. It's Linux, Apache, MySQL, and PHP. But very simple, very straightforward. And yet, the most comprehensive architecture diagram I could find was this one. And even I can tell that this oversimplifies a great deal and omits a great deal. Clearly, that's a lot more complicated looking than a simple LAMP stack architecture. I'm not going to dive into that architecture diagram and try to explain everything, even if I could. It was just sort of to demonstrate that when you're hosting at Wikipedia scale and the number of features and the number of integrations that Wikimedia hosts, things get rapidly much more complex. I'm going to focus on just one of those complexities, which is visual editor. So as most of you probably know, in a wiki, we have this concept well, in MediaWiki at least, it's called Wikitext, of a plain text format that is relatively friendly for humans to edit. And the reason for that is what we need to send to the browser is HTML, and editing that directly is decidedly not friendly. So the way this works is, you have a web form, you enter in your Wikitext, you mash save, and you're presented with the HTML representation of that document. And at the core of all this, obviously, is a conversion from Wikitext to HTML. When you want to go back and edit it again, you go back to the last edited version of the Wikitext document, you edit it, you click save, and you marshal that into HTML for the browser. What Visual Editor gives you is a WYSIWYG editor. What you see is what you get. So when you mash edit and Visual Editor is enabled, you stay on that HTML representation. Editor controls appear and allow you to select formatting, whether you're editing a section header or a paragraph, bullets, links, this sort of thing. And then when you mash save, the editor controls disappear. This is really nice. It's not a JavaScript hack. This uses HTML5's content editable. So it's a very nice editing experience. This is really great because as much friendlier as Wikitext is for editing HTML, it's still kind of off-putting to most people. So this really lowers the barrier to contribution. But it goes without saying that it also requires that we're able to convert from HTML back to Wikitext, because we have 15 years of history, 38 million articles in Wikipedia alone worth of history. A lot of people are still going to prefer editing Wikitext. We can't just change to editing HTML. It's a big ship, take a long time to steer. So we need to be able to go not only from Wikitext to HTML, but from HTML back to Wikitext. And that's not as simple as it might sound. One example of a complication there is history. We expect to be able to do character-based diffs between arbitrary revisions of a document. So if in the conversion from HTML back to Wikitext, you normalize any portion of the document outside of what the editor did themselves, then you create a dirty diff. So the way you do that is at the time that you're marshalling the Wikitext to HTML, for that given version, the given revision of Wikitext, you kind of evaluate as you go, what would it take to preserve this formatting on the round trip back from HTML? And you supply that information in the form of additional metadata. So if you look at this, this first line, this is an example in Wikitext of a wiki link, of an internal link to a page named foo in the same namespace that we're editing in. And the link text will be bar. But when marshaled to HTML, it's just an anchor. So there's really no way to tell it from one link type from another. So in this case, we pass an RDFA attribute that indicates that when we round trip back to Wikitext, that this should be a wiki link. A little bit more complex example, if the link text is the product of a template, we want to transclude that template into the final output. We don't want to take that output then and push that back into the Wikitext. We want to get the template back again. So in this case, we wrap that value, the text, the link value in a span with attributes to indicate that that's a template. And then we have this data parsoid attribute, this private attribute that stores the actual template itself. And in practice, in more complicated examples, that private attribute can actually get really, really verbose, can get right down to character and byte offsets in an effort to have all of the information necessary to reconstitute that original text formatting. So we do this conversion to HTML, this round-trippable HTML, with a stateless microservice called parsoid, which is written in Node.js. It exists specifically for this service, to take a specific revision of Wikitext and create the HTML representation that can then be edited and converted back to Wikitext without altering without introducing any non-normative changes. The reason this is an external service primarily is because Visual Editor is an extension. It's an add-on to MediaWiki, and because this wouldn't be a good general purpose solution for converting to HTML. Converting like this is computationally intensive, so it's slower. The output is larger, so it takes longer to transfer, which would make page load times higher. The DOM is just even more complex and takes browsers longer to load. So we targeted only at users who are going to need to edit that HTML, and we use a lighter weight conversion for the general case. Also, having it as an external service lets us scale it out horizontally. So this is one of those things that contributes to that extra complexity on that architecture diagram. Parsoid is stateless though, so we host it behind another service from Wikimedia called restbase, which is a sort of services aggregator that performs durable caching of responses. So it looks something like this. That durable caching occurs in Cassandra. We persist those response values in Cassandra. And there are other services that we aggregate behind restbase as well. Examples include mobile content service. We have Android and iOS clients, applications that exist to provide a more native feel for those platforms. Sometimes that involves transforming the content. The mobile content service does those transformations and then can persist those in restbase. So that's my use case. Let's look a little bit at Cassandra's use in that for this purpose. So we have 2 data centers. We use Cassandra's network topology strategy to distribute a total of six replicas, 3 each across 2 data centers. In Cassandra parlance, we also distribute within the data center across 3 racks. In reality, for us, the row is the level of infrastructure isolation we're looking for. That's where we have where we share common PDUs. So we can lose an entire row in a data center and still be available. We can lose an entire data center and be available. It's just really nice. We run 18 hosts, 18 physical machines, but we have a 54-node Cassandra cluster. So we have 3 times more Cassandra nodes than we do hosts, and I will expound on that in a little bit here. We use deflate compression in Cassandra, which is a little unusual. It's not the default. There aren't very many people using deflate, and we also get higher compression sizes, which I will explain as well. And it is a read-heavy workload for Cassandra, which probably comes as no surprise, given I described it as a durable cache. But 5 to 1 is maybe not as high a read-heavy as you would think. On every single document edit, we fire off an asynchronous job to prime the cache, hedging our bets against someone maybe wanting to edit that in Visual Editor. So the write rate is maybe a bit higher than you might expect. And this is kind of a second-tier cache to our CDN. So restbase is hit to produce this output only when there's a cache miss on the CDN. All right, so let's look at the data model. If you look at this in Cassandra DDL, like what you would use to create the table, and I'll limit this just to the HTML storage, and this is a bit oversimplified. We have these attributes: domain, title, revision, TID, and value. Domain is the Wikimedia site domain, so en.wikipedia.org, de.wikipedia.org, something like that. Title is the document title. Revision is the monotonically increasing revision ID supplied by MediaWiki. So whenever someone edits a document in MediaWiki assigns it a new revision. This is that revision. The TID value here, it's kind of a misnomer, I guess, is also a sort of revision. It's one that is created by restbase, and it is meant to indicate the revision of the HTML for that revision of document. And the reason this is necessary is that we do full page renders, and so there's always some sort of transcluded material in there. If you think in terms of, say, a template, if a template is edited somewhere centrally, every document that includes that template would then need to be re-rendered, even if those documents themselves didn't change. So it's sort of a revision of the revision. It's the HTML revision of the Wikitext revision. And then the blob, of course, value is where we store the HTML itself. The way these clustered primary keys work in Cassandra, it determines the layout of the data. So the first component of that parenthesized value is always the partition key. It's what determines placement in the cluster, determines distribution around the network. In this case, that is also a parenthesized value. It's the domain and title. It's like a two-tuple, a pair. So every domain title, unique domain title combination is used to determine placement within the cluster. These subsequent values set up a many-to-one relationship between themselves and the values that appear adjacent to the left. So for each unique domain title, we can have an arbitrary number of revisions. And for each unique domain title revision, we can have an arbitrary number of these TIDs, the renders. And since the value does not appear in that definition, for each unique domain title revision TID, there'll be exactly one value. And this also sets up ordering of the data. The order that the data is actually persisted on disk, so that it is ordered first by revision and then by TID. So if you select and limit one, you essentially get the most recent value. Another way of looking at that is like this. Again, for a domain and title pair, we can have one or more revisions, and for each revision, we can have one or more of the renders of that HTML. This is kind of important because this is the way the data ends up being laid out on disk, at least in each table file. The data is laid out like this in sorted order, which is important because of compression, for example. One thing that all general purpose compression algorithms have in common is that they look for repetition and attempt to store back references to a single copy of that repetitive material. That works well for us because most revisions, whether they're renders, individual HTML renders of a particular revision or the revisions themselves, it is most typical that the content changes between them very little, that the amount of repetition is very, very high. So Cassandra gives us this tunable chunk length KB that determines the size of data as it's being streamed off disk that will be given to the compressor implementation. So by widening that chunk length, we're able to find more of that repetition and bring the compression sizes down. Within reasonable limits, Deflate has a fixed 37K window size, so documents that exceed 37K, the HTML render, it starts to fall off rather quickly, the benefits you get from this. Which is why we've been looking at a compression algorithm called Brawley, which is relatively new, brought to you by the folks at Google. We've written a Cassandra implementation for it. I didn't have ready for this talk any formal results, anything I really felt confident to stand behind, but the initial results are very promising. We've done quite a bit of testing using settings that are comparable, that allow an apples-to-apples comparison between Deflate, and the results match up pretty well with the publicly posted comparisons of Brawley to Deflate, which is that you get smaller compressed sizes at a lower computational cost. So it's a win either way. But one of the things that Brawley will let you do is it'll let you open that window up. And so now we can kind of almost treat it like a binary differ. And one of the examples, I'll post these slides afterwards. I have links to some tickets here. There's a little bit more detail in this ticket on the slide. But one of the examples there were documents that were 250K in size, and with a 4 meg chunk length and a corresponding Brawley window size, we were able to get compressed sizes of 1.73% of the original, which is really, really good. Okay, so compression has been a pretty important topic for us, something we spend a lot of time on. Compaction is also something that's occupied a fair amount of our time. Compaction in Cassandra is basically the price you pay for having a log-structured storage engine. It's an asynchronous background process that attempts to keep up with the writes that are occurring and reorganize the data to make it more optimal for the reads. Cassandra presents a metric, a histogram, called SS tables per read. It's essentially the number of SS tables that need to be contacted in order to satisfy reads. And we watch that very closely because read latency tracks pretty closely with the number of SS tables that you have to sort of merge together to get the picture of for your results. And it speaks to the efficacy of compaction. So with compaction, at a minimum, what you want to do is get the total number of files down, minimize the bound the number of SS table files you have. If possible, you'd like to order them in such a way that the results are closer together. Cassandra has 3 different kinds of compaction strategies: size-tiered, leveled, and date-tiered. Size-tiered is the simplest. It just combines files of similar size together to create fewer, larger files. But it's completely oblivious to column distribution. Leveled compaction, which is the compaction strategy we started out with, is perhaps the most optimized for reads in like the general sense. It uses files of fixed sizes and organizes them in levels where each successive level has an exponentially increasing number of SS table files. But the files within each of these levels are non-overlapping. So if you imagine a simple point query, that tends to be the SS tables per read for level compaction tends to be no worse than the number of levels, which is very good. It's the downside of that, and the reason I say we used to use it, is that the compaction throughput is very high. It's just constantly busy, madly compacting data in the background, so it uses a lot of I/O. Which brings us to date-tiered compaction, which attempts to game the fact that we know the timestamps of the data that was written. And so if your data set is total ordered, if your values that you're storing and querying against are only ever increasing, then so is time. And so if we compact together data according to similarity in time, tiers based on the date time, then that will also place your data closer together. So given the sort of MVCC structure of our data model, this seems like an absolute win. Like this should be the one for us. It has turned out in practice, though, that is not the case. I would try to explain in detail why it is not the case, but I'm worried I would just get it wrong. It's very hard to reason about the way DTCS actually works. What I can tell you is that the optimizations are easily defeated by any kind of out-of-order write. And in Cassandra, it is almost, I don't want to use hyperbole, but it feels almost impossible to avoid, any out-of-order writes. So read repair, for example, is something we usually rely on to keep the integrity of the data. Read repair will create out-of-order writes, and it will essentially defeat all the optimizations provided here. Updates of the data of any kind produce out-of-order writes. Again, I've got a ticket here. If you'd like to read like a more detailed explanation of how it has failed in our specific environment, you can go look at that. But the summary is we're currently using DTCS, and it does not work well for us. What we're planning to do about that is when these optimizations are defeated, you're essentially left with one date tier. It kind of flattens the structure out. And since DTCS does size-tiered compaction within those tiers, we're essentially running size-tiered compaction. So we may just switch to that to be clear about how this is working. There's also another compaction strategy that exists outside the Cassandra tree right now, but is gaining a lot of popularity, called time window compaction strategy, that attempts to build the same sort of optimizations that, again, if you ordered by time and your data set is meant to be total ordered, then it will place your results near each other. So we're planning to take a good look at that. One of the things we may just do is just lower node density, just reduce the size of the individual Cassandra nodes by deploying more of them. And the reason that works is, again, we're interested in SS tables per read. And so if the efficacy of the compaction strategy is poor and the number of SS tables versus the total number of SS tables that we read from is too high, well, then one way of solving that is just to simply reduce the total number of SS tables, which reducing the data set size will do. All right, so moving on, garbage collection. It's a Java app. It's latency sensitive. It's got a lot of throughput, so obviously garbage collection has been an issue. That should come as no surprise, which is one of the reasons that we have been fairly early adopters of G1 GC. We've been using it for quite a while now. G1 is short for garbage first. It is meant to be a successor to concurrent mark sweep. It is different in that it is an incremental, parallel compacting collector. So it's always kind of looking for the low-hanging fruit and copying regions from one location to another to keep the heap continually compacted. And it works really well. In fact, it works fantastic, particularly if you can give it a little more memory than what you might normally need. It can kind of paper over some of the sort of impedance mismatches between the way an application like Cassandra works and generational theory. The one exception, the one problem we have had is what and this is the G1 terminology, humongous objects, is with these so-called humongous objects. So what G1 does is at startup, if you have not explicitly specified otherwise, it divides the heap up into, it makes its own determination to divide the heap up into some number of regions of some size. If the objects that you're allocating to these regions are 1/2 the size of the region or larger, then it sort of special cases that. It treats them exceptionally. It will only allocate one object per humongous region, and these humongous regions have to be contiguous. So if you have too many of them, then the usage of the heap will be very inefficient. You'll waste a lot of heap, and you will fragment the heap. They're meant to be treated exceptional, so the number of them should be exceptional. In our case, we saw, with 12 gig heaps, we saw region sizes being calculated at 4 megs, which meant anything 2 megs or larger was being allocated as humongous. There were a bit too many of them, and it kind of destroyed the efficiency of the collector. So we have since set that up to 8. That's something to keep in mind. Enable GC logging, have a look at that. It's pretty obvious when you're getting too many humongous allocations. Okay, so on node density. If you talk to anybody in the Cassandra community, Pretty much everybody who has any experience with Cassandra will always recommend that if given a choice, you should run more nodes of a smaller size than larger nodes, than fewer larger nodes. It's not really documented anywhere. It's not in any of the formal documentation. And it's probably because, rightfully so, anybody who says this ought to be ashamed. It kind of ignores the realities of growing hardware. Hardware is becoming more and more capable, and data center costs that you can't vertically scale across available hardware. The issues that we've had running nodes that were too dense are quite numerous, but I'll just limit them to the ones that I've discussed so far. Again, if the efficacy of compaction is not good, then lowering node density lowers the data set size under control of a single node, and that means that the number of SS tables contacted will be smaller. Also, the throughput that is created by compaction will be less. And if throughput for compaction is high, along with all the rest of the throughput that's higher, will in turn make GC worse if your node density is too high. So we have had problems with node density being too high and had that create issues for us, and we've had to deal with it. And that's why on that earlier slide I mentioned that we have 3 times as many Cassandra nodes as we do hosts to run them on. And how we deal with that is we spin up processes. So we use Puppet in our environment, so we just use Puppet to create multiple configuration directories that reference multiple data file directories, and we have multiple systemd units that just spin up multiple processes with no effort to limit contention or anything. And to make matters worse, we have them all running on one single shared RAID 0 array. So we have quite the impressive blast radius going on here. We lose 1 disk, we lose the array, we lose 5 terabytes of storage, and three Cassandra nodes go down. Probably not the best. What I wish we had done was used a mechanism designed for allocating hardware resources to processes like virtualization, containers. Just purchasing blades would have been better, I think, to get to keep that 1-to-1 host parity if necessary. Anything but what we did, probably. And so to kind of wrap things up, what has worked well for us with Cassandra in general is sort of the core features. The things that differentiate Cassandra from the other databases are still make it the right choice. The way tunable consistency works to let us trade away point-in-time consistency in order to buy availability, the multi-data center awareness, the visibility. It's very well instrumented, so it makes it rather easy if you need to dig in and troubleshoot something. It's getting to the point where Cassandra's reached that kind of critical mass. There's a ubiquity there. It makes it much easier to find libraries and supported applications, and to find help if you search the web, or to find people who are willing to share their experiences. All in all, it has been, if I sounded critical at any point, it has worked out really well, and most of that is just attributed to sort of the core functionality. What isn't so good is usability. And I probably would have balked at this a year ago. I'm sure that many of my colleagues within the project would balk at it and probably rightfully point out that usability is so much better than it used to be. That actually makes it worse because usability is still pretty bad. So that just means it was worse at one point. Compaction is maybe this is perhaps getting overcritical, but compaction is a pretty good example. The fact that you have to worry about this at all, I think, is that it's more than simply an implementation detail is kind of bad from the usability standpoint. That you have to not only understand your data model and your access patterns, which I think is reasonable, but you also have to thoroughly understand those compaction strategy algorithms, and really get low level into the to the analysis of how they're working and the troubleshooting and tuning. Feels very much like in any other application, like that ought to be an implementation detail. Not to say that that's an easy problem to solve, but it does make Cassandra not that usable. controlling streaming for like bootstraps and decommissions and this sort of things really like crazy wonky. I mean, your concurrency, your available throughput is a function of how many nodes are available to stream. Like there's no per node concurrency. So you can either overwhelm the node if you don't throttle it down, or you can end up with terabytes of data to transfer at just a few megabytes per second. And the only option would be to increase the number of nodes. That's bizarre to me. But it took, like again, getting on the other side of the fence before I realized that was even an issue. JMX is a miserable way of having to interact with the system for monitoring and management. And full disclosure, I probably had more to do with this decision in the early days of Cassandra than anybody else. And you probably lay this at my feet more than anyone else's. But it just means that everything has to, it's kind of a Baroque, way of dealing with, way of coding against Cassandra anyway. But it's very, very much limited to Java. So, this is the kind of thing where I think, if it were open to dynamic languages, we'd probably see a lot better tooling for Cassandra at this point. And then, as I mentioned, the vertical scaling story is just awful. We run 16 core machines with 128 gigs of memory and 5 terabytes of disk space. And we simply cannot fully utilize that hardware in a good way, in a performant way, where we're forced to run more than one Cassandra process on the machine just to be able to fully utilize that hardware. And then to get away from the bad and into the ugly, upgrading between major versions has been really, really painful. It has always been painful. I was kind of surprised to see that it's just still as painful. Some of this is kind of just normal quality control issues, things that somehow manage to get by without getting fixed. Others are just like there's just no excuse for it. Like what seems like wholly arbitrary changes to metric names, for example, so that you have to go in and retool all your graphs because, I don't know, because somebody wanted to change the case of the capitalization of a metric name or something. Really painful, the upgrade process. I know a lot of people have related to me that they don't even consider Cassandra upgradable. I wouldn't go that far, but I do know more than one person who's actually said that it is their policy, it has been their policy since the beginning, and they're standing by it, that they would just stand up a new cluster and migrate to it. And then the release process, or the quality of releases is bad. It's always been bad. It's kind of been, the folklore that, the sort of the passed down knowledge for people who've been around, only to upgrade on like the 6th release. Just sit out the first 5 because there's going to be lots of problems. Let other people shake that out. Like so bad to the point that there's nobody shaking out those bugs because everybody's waiting for the .6. And the problem here has always been, one of trying to balance the amount of features and the churn in the code, with bug fixes and maintaining a stable trajectory. So we adopted this new release process, modeled after Intel's tick-tock, that makes even-numbered releases mean one thing and odd-numbered releases mean another, and more feature-type stuff goes into one, and more bug fixes go into the other. And if this has done anything to solve the problem, I don't think you could prove that one way or the other. All it's done is obfuscate where that sweet spot is, where it is that where the stability that you're looking for lies. And anybody that disputes that could just look on the Cassandra mailing list at all of the people who ask, what version should I be running? It's maddening trying to figure that out. So that has definitely not worked out in my opinion. And so with that, I think I have a few minutes left for questions if anybody's got them.
Thank you, Eric. Any questions? Okay.
I was wondering how painful scaling out, like adding nodes to a cluster is for...
That's easy. Yeah,
okay.
Scaling out horizontally is easy.
But the impact of transfers or anything like that between nodes when you add in one, does that have any...
Sorry, repeat that last part.
Does the impact of transfers from one node to another when you add nodes have any impact, or...?
Well, they don't need to.
Okay.
I mentioned from a usability standpoint, streaming. if you're using a rack-aware data center setup like we are, what Cassandra does when it builds a stream plan for a bootstrap to add a new node is it looks for the minimal number of nodes that have the replicas it needs that are nearest to it. So if you're running in a rack-aware data center-aware configuration, that's the nodes that are in the same rack. So if, for example, you have 2 nodes, or you're bootstrapping in the second node, your stream concurrency is 1. And if you're using compression, then that one thread can become bottlenecked on CPU utilization. We see about 4 megabytes per second. If you have several terabytes of data to transfer at 4 megabytes per second, it's going to take a very long time to do. The only way to get that throughput up is to have more nodes in that rack that can be involved in the stream. But if you have too many, then it could be overwhelming. The stream concurrency then goes up. But that's okay because you can throttle that down by adjusting the outbound throughput of all of the nodes that are streaming to the node. So if you're bootstrapping new nodes into a rack, you have to change all of the outbound throttles, all the outbound throughputs as you add each new node, and the total available throughput changes. So yeah, the usability story is a mess there.
Okay. Any other questions?
Hi. Looks like you've had your share of problems with Cassandra. If you were to do it all over again, would you choose Cassandra or would you choose anything else?
Yeah, I don't really know. Again, some of the features that were important. I mean, we're trying to hit a certain performance targets, and we're trying to do it at a certain cost. And we're trying to we're trying to end up with like an active setup across multiple data centers, and we're trying to maintain certain availability. And I don't know of any alternative that would have solved all of those in any better way. So I don't know that it changes the what I would do if I could go back again. I also came into this after it was already deployed, so it wasn't a decision that I influenced either way. But I don't really know of an alternative that would have been better. Of course, if somebody knows of an alternative that would be better, I'd be happy.
Thank you.
Hello. To what extent do you think are the vertical scaling problems that you experienced are attributable to Java, rather to Java than to Cassandra itself? Because the garbage collection and for example, the pointer compressions are problems that every Java process probably has.
Yeah, definitely. I think there's kind of an impedance mismatch between an application like Cassandra and any garbage collected language. People are pretty quick to jump on Java and GC issues, but I think it probably has one of the most robust set of garbage collectors of any language. But it's just kind of a mismatch between that kind of application and a garbage collector. And generational garbage collectors operate on the premise that everything is either very, very short-lived or very long-lived, perhaps for the lifespan of the application. And Cassandra's got a lot of middle ground there. It's got a lot of sort of medium-lived objects that kind of get, you have the potential to be prematurely tenured out of young gen, and which really screws up the efficiency. And then on top of all that, it's extremely latency sensitive because it's a database. So even if the pause times aren't really that bad under like for most typical applications, just inconsistent pause times is a problem for a database, even if the pauses themselves aren't that bad. So yeah, some of that is definitely JVM. And Cassandra has done a lot of there's been a lot of interesting like off heap optimizations in Cassandra. A lot of good work to make that less of a problem.
Thanks.
We are at the top of the hour, so is it short question that you've got? Okay.
Well, maybe trivial. How do you search within Wikimedia? So how is that implemented?
I'm sorry, I did.
The search. How is searching in Wikimedia implemented?
Can search be implemented in Cassandra? Not really. I mean.
I believe the question was what technology is used for the search functionality in Wikipedia.
Oh,
is it right?
Yeah, I'm probably not the best person to ask. I know there's a I believe, in MediaWiki it's Cirrus Search, but under the Wikimedia infrastructure we also use Elasticsearch.
Okay, we need to give time for next speaker to set his session up. Thank you, Eric, once again. And if anyone wants to talk.